Okay, folks, what we have here is we'll be looking at spectroscopy. Okay, so this section is on spectroscopy. Now, what we have here is called the electromagnetic spectrum. Right, the electromagnetic spectrum, and this electromagnetic spectrum originates from our sun. Okay, our sun is the one that produces all of these things that you're seeing on this screen. So we have at the end here we have gamma rays. Okay, so these are gamma rays, and then on the other end we end up with radio waves. What I want you to notice is in all of this there are something called wave numbers, okay, wavelength, and there is something called frequency. Okay, now what is the relationship between wave numbers and frequencies? All right, so what we're going to do is I'm just going to explain this to you. Apparently all of these waves that come from the sun move in waves. Okay, exactly. So all of this that comes from the sun moves in waves. Okay, so for example, let's say they move something like this. Okay, so the distance between one peak here and another peak here, this is called a wave number. This is a wave number. Okay, or you can even do it from here to here. This is a wave number, right? But we'll just focus on the top part now. Then we also have waves that look like this. Okay, let's say we have waves that look like this. Okay, so in this case this would be the wave number. Right, so let's call this A. All right, this is B. Okay. And then we also have waves that move, let's say like this. Okay, something like that. Not very good, but I think you get the point. So let's say we look at this distance over here. This distance is C. Okay, so what I want you to notice in these pictures that I've drawn here is the wave C is smaller than wave A, and A is smaller than B. You see this? Okay, so they are smaller in that way. Correct? So if this picture is taken in 1 second, let's say from here to here is 1 second. All right, this picture is taken in a time frame of 1 second. Then we can relate this to frequencies. Frequency, if the traditional thing here is frequency is the number of waves. Okay, number of waves in 1 second. Right, in 1 second. So that's what frequency is. So if we look at this, right, we will notice that the frequency, okay, or in physics we use the symbol V, frequency of C is greater than A. The frequency of A is greater than frequency of B. Okay, so in terms of frequency meaning how often something happens, right? Then what we can do is I can relate all of this together to something else. The energy of C is greater than the energy of A. The energy of A is greater than the energy of B. Right? So that's how the relationship works. So if this is the wave pattern in every second, the energy content of C is the greatest. It has the greatest amount of energy compared to the other two. Okay, so this is what we call wave. So the moral story here is this. You see, when all of this comes from the sun, they all bring different amount of energy. Okay, they bring different amount of energy. So what scientists have learned to do is they have learned to harness these wavelengths to do analysis, either qualitative analysis, meaning to know if something is there, to quantitative analysis, meaning how much of it is there. Okay, So in this part, under spectroscopy, we are going to be looking at some of the uses of the electromagnetic radiations to do analysis. Okay, to do analysis. And then in this part that you can see here, 400 nanometers, 400 nanometers to 700 nanometers. Okay, this is the visible region. This is where our eyes can see. Our rod cells and cone cells in our eyes are able to detect anything within this part. Okay, anything within this part our eyes can detect. Anything more than that, anything less than that, we cannot detect. All right, so this is what spectroscopy is about, is using these wavelengths. Okay, now in any spectroscopic technique, right, generally in any spectroscopic technique, there is always one light source. Okay, there is always one light source. So light source, or we can call this a radiation source. Okay, radiation source. Now this light source or radiation source will produce the wavelengths that we want. Okay, it will produce a wavelength. So let's say if we are talking about something in the visible region, it can produce wavelengths from, let's say, 400 nanometers to 800 nanometers. Oops. Okay. Nanometers. All right. Often the light source itself does not produce that, but there is another device in the pictures is drawn as a triangle. This is called a monochromator. Now basically it is the job of the monochromator to select. This is to select the desired wavelength. That's actually the job of the monochromator. Okay, then what we have is we have our sample. This is where our sample is kept, and then we have a detector. Okay, so this is the basic setup of most spectroscopic techniques. Okay, most spectroscopic techniques will have this. We'll have a radiation source, we'll have a sample and a detector, but of course there's a monochromator to select the wavelength. All right, so what happens in most cases is there is a radiation that is produced. Okay, passes through here and then comes out over here. So often what we do is we assume that this radiation is 100%. What before it enters the sample, it is 100%. Okay, when it comes out from the sample, what will happen is there is a possibility that some of this radiation will be absorbed by the sample. So let's say the radiation that comes out is 92%. So this means that 8% is absorbed. Okay, 8% has been absorbed. That's basically what it means. So what is our job is? Our job is to relate what is 8%. What does this mean in terms of molarity? Let's say mole per liter. What is this? So we need to be able to relate what is 8% to molarity, right? But let's say you put in 100%, and what comes out is also 100%. So if you put in 100% and what comes out is 100%, meaning it means that there is nothing absorbing. Okay, there's nothing absorbing, which means that whatever you're interested in is not there. Okay, whatever you're interested in is not there. So this is qualitative. Qualitative, basically you want to know whether it's there or it's not there. In this case, there is none. Okay, then there is also a possibility that when the light passes through, it could be absorbing, let's say 88%. So what does 88% mean? It basically means that Wow, it means that 12% absorbed. Okay, so earlier was 8%, now is 12%. So if you look logically, right, 8% versus 12%, 12% is greater, right? So this means that there is higher concentration here. So the percentage, the amount absorbed, okay, is proportional to concentration. Okay, so this is important. So the amount which is absorbed, the amount of light, okay, amount of radiation, or let's say light. Okay, the amount of radiation or light which is absorbed is related to concentration. That's the relationship. So this is how spectroscopy generally works. All spectroscopic techniques generally work the same way. Okay, same way. So let's move on here, and then I'll just explain this to you. So where are we? Okay, here we go. So this is what it was. Okay, everything that I told you is here. So this is what I meant by the light source, and then you have a monochromator. All right, you have a monochromator that selects the wavelengths, and then you have a sample and you have a detector. Okay, so that's basically how it works. Now let's say, for example, this is a color wheel. All right, this is a color wheel. Okay, so in a color wheel, right, something that appears blue, let's say the copper sulfate. All right, we have let's say we have copper sulfate. Oops, change color. Okay, let's say we have copper sulfate. It contains copper ions. Copper ions are often blue. Okay, they are blue in color. And the reason why they are blue in color is because they absorb. Okay, we'll do the color wheel here. You see this part here, this is blue. So let's say copper is here, because they absorb the orange part of the spectrum. All right, so they absorb all wavelengths starting from 580 nanometers to 620 nanometers. They absorb all of this. So when they absorb anything which is from 580 to 620, what remains, what comes out, what appears is blue in color. All right, so if I want to analyze copper, it is best that I use 580 nanometers to 620 nanometers. That's the best wavelength for me to use if I want to analyze copper. So which means that if I have a sample which contains copper ions, that's the wavelength that I should be using. Let's say if I want to analyze chlorophyll, okay, we know chlorophyll, or leaves. Okay, let's say leaves are green in color. Okay, let's say this part here, I want to analyze leaves. So the best wavelength for me to use if I want to analyze leaves will be the opposite side, which is 620 to 800. Okay, so if there's something which is yellow, and I want to analyze it, the best wavelength for me to use would be anything from 400 to 430. That's basically how it works. Now when we come back to copper here, right, so I just told you to analyze copper, 580 nanometers to 620 nanometers is the best wavelength. Okay, but within this wavelength itself, there is an even better wavelength that we can use. So this is where a graph like this will come up. Okay, let's say. Okay, so let's say if we start from 580 here, and then we end at 620 here. Okay, nanometers. If we do that, right, what we do is we pass all of the wavelengths. Starting from 580 nanometers all the way to 620 nanometers. From 580 to 620. We might get a graph that looks something like this. Okay. You might get a graph like this. And if you analyze this graph, you will notice that at this point, right, so this is absorbance. Okay, absorbance. You will notice that this part here, there is maximum absorbance. This is maximum absorption. So if you go down here, maybe, okay, I'm going to look at this roughly. Let's say this is 590. Okay, 590, and then let's say this is maybe could be let's say 605. Let's say that. What we can say is at 590 here, this is where maximum absorption, absorbance takes place. Okay, takes place here. So when we come back to copper sulfate, right, instead of using 580 to 620, instead of using all of it, what we can do is we can just focus on 590. We just use 590. We don't use 580, we don't use 610, we use 590. Why? Because at 590 there appears to be a maximum absorption taking place. Okay, maximum absorption. Okay, like in this graph here. All right, so it says absorption maxima, so which means that for this, whatever sample this is, this picture here, 471 seems to be the maximum absorption. So if I want to analyze this, okay, it talks about lycopenes, right? If I want to analyze lycopenes, the best wavelength for me to use would be 471. Okay, 471 would be the best wavelength for me to use. Okay, so that's how I can analyze lycopene. All right, so it says here lycopenes absorb in the region of 440 to 500. 440 to 500, what color will that be? All right, what color will that be? Okay, so it says lycopenes are usually red orange compounds, so it absorbs at 440. Let's go back to the color wheel. Let's have a look at this. Where's the color wheel? Oh, sorry, I got it wrong. Color wheel was right just now. Okay, sorry, it says 440. All right, 440 to 500. Okay, absorbs 440 to 500. 440, there, here it is. All right, somewhere around here, right? So it absorbs at this region. So what color would lycopene be? It absorbs light in the blue-green region. This part here, right? This part, it absorbs somewhere here. So what will lycopene look like? It will look like something like red orange. All right, so yeah, red orange solution. Okay, so it will appear like red and orange. So that's basically what it is. Okay, so idea here is this: if let's say we are using UV visible spectroscopy. Okay, so now we're talking about UV visible spectroscopy. If we use UV visible spectroscopy, UV, which means that we are actually starting at 200 nanometers to 400 nanometers. Okay, this is UV, and then from 400 all the way to 800, okay, nanometers, this will be visible. Let's say you are analyzing something which has color. All right, if it has color, okay, it has color, then we are going to be focusing on this region here. We use wavelengths in this region. But let's say if you're analyzing something that has no color, is colorless, right, then we're going to be focusing on this region here, starting from 200 to about 400. So colorless compounds, if anything which is colored, like a clear solution, we will use a wavelength in the region of 200 to 400. But if it has color, then it's going to be 400 to 800. That's the wavelengths that we use. Okay, so that's what visible spectroscopy is, UV visible spectroscopy. All right, now in the lab, maybe in a week's time or 2 weeks time, we'll be doing this. We'll be doing an analysis of copper solutions. Okay, so in that lab we will be using a wavelength which is 590 nanometers, and I hope that you guys will know why we're using 590 nanometers, because it gives maximum absorption. Okay, so this is UV visible spectroscopy, right? UV visible spectroscopy is here. So basically in this part, what we're doing is we're just using the UV or visible part of the spectrum to analyze substances. Now before we end this, I just want to let you know, just now I told you that the energy is absorbed, right? So when we pass energy, okay, the energy is absorbed. So let's say what comes in here is 100%, and what goes out here could be, let's say 78%. Okay, so which means that 22% is absorbed. Okay, so who is absorbing this? Okay, who is absorbing this energy? Very often it is the electrons in the molecule, right? The electrons in the molecules. It could be electrons in the bonds, it could be electrons in the molecule itself, but whatever it is usually the electrons are the ones who are absorbing the energy. So when we say we are passing a certain wavelength of light or this and that, we are actually passing energy, and that energy is what is being absorbed. Okay, all right, we'll stop here. Then maybe the next part I want to talk to you about is about calibration. Okay, it's about calibration graphs. So maybe that one we'll do another video.